In this lecture, we start our discussion of continuous random variables. We will focus on the case of a single continuous random variable and will describe its distribution using a so-called probability density function, an object that will replace the PMFs from the discrete case. We will then proceed to define the expectation and the variance of a continuous random variable, and we'll see that their basic properties remain unchanged. There will be one new concept, the cumulative distribution function, which will allow us to describe in a unified manner both discrete and continuous random variables, even so-called mixed random variables that have both a discrete and a continuous component. In the course of this lecture, we will also introduce some of the most common continuous random variables: uniform, exponential, and normal. We will pay special attention to the normal distribution and the ways that we can calculate the associated probabilities.
In this segment, we introduce the concept of continuous random variables and their characterization in terms of probability density functions, or PDFs for short. Let us first go back to discrete random variables. A discrete random variable takes values in a discrete set. There is a total of one unit of probability assigned to the possible values, and the PMF tells us exactly how much of this probability is assigned to each value. So we can think of the bars in the PMF as point masses with positive weight that sit on top of each possible numerical value. And we can calculate the probability that the random variable falls inside an interval by adding all the masses that sit on top of that interval. So for example, if we're looking at the interval from A to B, the probability of this interval is equal to the sum of the probabilities of these three masses that fall inside this interval. On the other hand, a continuous random variable will be taking values over a continuous range, for example the real line or an interval on the real line. In this case, we'll still have one total unit of probability mass that is assigned to the possible values of the random variable, except that this unit of mass is spread all over the real line, but it is not spread in a uniform manner. Some parts of the real line have more mass per unit length, some have less. How much mass exactly is sitting on top of each part of the real line is described by the probability density function, this function plotted here, which we denote with this notation. The letter F will always indicate that we're dealing with a PDF, and the subscript will indicate which random variable we're talking about. We use the probability density function to calculate the probability that x lies in a certain interval, let's say the interval from A to B. And we calculate it by finding the area under the PDF that sits on top of that interval. So this area here, the shaded area, is the probability that x takes values in this interval. Think of probability as snowfall. There is 1 pound of snow that has fallen on top of the real line. The PDF tells us the height of the snow accumulated over a particular point. We then find the weight of the overall amount of snow sitting on top of an interval by calculating the area under this curve. Of course, mathematically, area under the curve is just an integral. So the probability that x takes values in this interval is the integral of the PDF over this particular interval. What properties should the PDF have? By analogy with the discrete case, a PDF must be non-negative because we do not want to get negative probabilities. In the discrete case, the sum of the PMF entries has to be equal to 1. In the continuous case, x is certain to lie in the interval between minus infinity and plus infinity. So letting a be minus infinity and b plus infinity, we should get a probability of 1. So the total area under the PDF, when we integrate over the entire real line should be equal to 1. These two conditions are all that we need in order to have a legitimate PDF. We can now give a formal definition of what a continuous random variable is. A continuous random variable is a random variable whose probabilities can be described by a PDF according to a formula of this type. An important point. The fact that a random variable takes values on a continuous set is not enough to make it what we call a continuous random variable. For a continuous random variable, we're asking for a bit more, that it can be described by a PDF that a formula of this type is valid. Now, once we have the probabilities of intervals as given by a PDF, we can use additivity to calculate the probabilities of more complicated sets. For example, if you're interested in the probability that x lies between 1 and 3, or that x lies between 4 and 5, so this is the probability that x falls in a region that consists of two disjoint intervals. We find the probability of the union of these two intervals by additivity, by adding the probabilities of the two intervals, since these intervals are disjoint. And then we can use the PDF to calculate the probabilities of each one of these intervals according to this formula. At this point, you may be wondering what happened to the sample space in all this discussion. Well, there is still an underlying sample space lurking in the background, and different outcomes in the sample space result in different numerical values for the random variable of interest. And when we talk about the probability that x takes values between some numbers a and b, what we really mean is the probability of those outcomes for which the resulting value of x lies inside this particular interval. So that's what probability means. On the other hand, once we have a PDF in our hands, we can completely forget about the underlying sample space, and we can carry out any calculations we may be interested in by just working with the PDF. So, as we move on in this course, the sample space will be moved off stage. There will be less and less mention of it, and we will be working just directly with PDFs or with PMFs if we are dealing with discrete random variables. Let us now build a little bit on our understanding of what PDFs really are by looking at probabilities of small intervals. Let us look at an interval that starts at some a and goes up to some number a plus delta. So here delta is a positive number, but we're interested in the case where delta is very small. Let us look at the probability that x falls in this interval. The probability that x lies inside this interval is the area of this region. On the other hand, as long as f does not change too much over this little interval, which will be the case if we have a continuous density f, then we can approximate the area of this region by the area of a rectangle where we keep the height constant. The area of this rectangle is equal to the height, which is the value of the PDF at the point A, times the base of the rectangle, which is equal to delta. So this gives us an interpretation of PDFs in terms of probabilities of small intervals. If we take this factor of delta and send it to the other side in this approximate equality, we see that the value of the PDF can be interpreted as probability per unit length. So PDFs are not probabilities, they are densities. Their units are probability per unit length. Now, if the probability per unit length is finite and the length delta is sent to 0, we will get 0 probability. More formally, if we look at this integral and we let b to be the same as a, then we obtain the probability that x is equal to a, and on that side we get an integral over a zero-length interval, and that integral is going to be 0. So we obtain that the probability that x takes a value equal to a specific particular point, that probability is going to be equal to 0. So for a continuous random variable, any particular point has 0 probability. Yet somehow, collectively, the infinitely many points in an interval together will have positive probability. Is this a puzzle? Not really. That's exactly what happens also with the ordinary notion of length. Single points have 0 length, yet by putting together lots of points, we can create a set that has a positive length. And the final consequence of the fact that individual points have 0 length. Using the additivity axiom, the probability that a random variable takes values inside an interval is equal to the probability that a random variable takes a value of a plus the probability that a random variable takes a value of b plus the probability that a random variable is strictly between a and b. According to our discussion, this term is equal to 0. And this term is equal to 0. And so we conclude that the probability of a closed interval is the same as the probability of an open interval. When calculating probabilities, it does not matter whether we include the endpoints or not. Let us now give an example of a continuous random variable, the uniform random variable. It is patterned after the discrete random variable. Similar to the discrete case, we will have a range of possible values. In the discrete case, these values would be the integers between a and b. In the continuous case, any real number between a and b will be possible. In the discrete case, these values were equally likely. In the continuous case, at all points we have the same height for the probability density function, and as a consequence, if we take two intervals that have the same length, then these two intervals will be assigned the same probability. Intuitively, uniform random variables model the following situation. We know that the numerical value of the random variable will be between a and b, but we know nothing more. We have no reason to believe that certain locations are more likely than others, and in this sense the uniform random variable models a situation of complete ignorance. By the way, since probabilities must add to 1, the area of this rectangle must be equal to 1, and therefore the height of this rectangle has to be 1 over b minus a. So that we have a height of 1 over b minus a, we have a length of b minus a, so the product of the two, which is the area, is equal to 1. Finally, here is a more general PDF, which is piecewise constant. One thing to notice is that this in particular tells us that PDFs do not have to be continuous functions. They can have discontinuities. Of course, for this to be a legitimate PDF, the total area under the curve, which is the sum of the areas of the rectangles that we have here, must be equal to 1. With a piecewise constant PDF, we can calculate probabilities of events fairly easily. For example, if you wish to find the probability of this particular interval, which is going to be the area under the curve, that area really consists of two pieces. We find the areas of these two rectangles, add them up, and this gives us the total probability of this particular interval. So, at this point, our agenda moving forward will be twofold. First, we will introduce some interesting continuous random variables. We just started with the presentation of the uniform random variable. And then we will also go over all the concepts and results that we have developed for discrete random variables and develop them again for their continuous counterparts. We now start with our agenda of developing continuous counterparts of everything we have done for discrete random variables. Let us look at the concept of expectation. In the discrete case, we have defined expectation as a weighted average of the values x of the random variable, weighted according to their corresponding probabilities. In the continuous case, we define expectation in a similar way, as a weighted average of the possible values of x, weighted according to the corresponding value of the density. Points where the density is higher, for example here, will receive a higher weight in this calculation. But of course, since we are averaging over a continuous set, the summation will have to be replaced by an integral. This will be a recurrent theme in this unit. Definitions or formulas for the continuous case look exactly like the discrete ones, except that PMFs are replaced by densities, as here, the PMF is replaced by a density, and summations are replaced by integrals. The intuition is usually the same in both the discrete and the continuous case. However, the intuition is usually much clearer, much easier to visualize in the discrete case. So the best strategy is to make sure to understand fully the intuition for the discrete case and just rely on it. At this point, let me add some fine print, a mathematical side point. This integral, or the expectation, will not be always well defined. For this integral to make sense, we will need to make the assumption that the integral of the absolute value of little x, weighted according to the density, gives us a finite result. Unless we explicitly say something different, we will always assume that we're dealing with random variables that satisfy this condition, and so the expectation is well defined mathematically. Coming back to the big picture, regarding expectations, the intuition remains the same as in the discrete case, that the expectation represents the average of the values we expect to see in a very large number of independent repetitions of the experiment. In fact, there are also theorems to this effect, but these will have to wait until later in this class when we study limit theorems. Another intuitive interpretation that is true for both the discrete and the continuous case is that the expectation corresponds to the center of gravity of the probability distribution. So in this diagram, it might be somewhere around here. And similarly, for the continuous diagram, the center of gravity might be somewhere around here. And if it happens that the distribution, the PMF or the PDF, happens to be symmetric around a certain point, then that point will be equal to the expectation. Expectations of continuous random variables have all the properties you might expect. For example, non-negative random variables have non-negative expectations. Random variables that lie inside an interval have average values or expectations that also lie inside the same interval. The derivation is exactly the same as for the discrete case. There is also an expected value rule. In the discrete case, it took on this form. In the continuous case, we obtain an analogous form in which the summation is replaced by integral, and instead of weighing according to the PMF, we now weigh according to the density function. The derivation of the expected value rule for the continuous case is a little more complicated than the one that we gave for the discrete case, but it's sufficient for us to know that it is true and that it has an intuitive meaning that runs along the same lines as the intuitive meaning that we had for the discrete case. As an instance of how we might apply the expected value rule, if you wish to calculate the expected value of the square of a continuous random variable, you would proceed as follows. You would integrate over the entire real line the value of the function, which is x squared in our case, weighted according to the density. Finally, a most important property of expectations is linearity. Linearity is still true for continuous random variables as well, and the way it is derived is exactly the same as in the discrete case, namely we apply the expected value rule to this function of the random variable x and separate out the various terms. The story regarding variances is exactly the same as in the discrete case. We define variances using the same definition, and of course here mu stands for the expected value of the random variable x. To calculate the variance, we can use the expected value rule, which takes this form in the continuous case, and we apply the expected value rule for the case where we're dealing with the expected value of this particular function, so that in this instance the function g of x is x minus mu squared. So by applying the expected value rule, we obtain the integral from minus infinity to infinity, the function g of x, weighted according to the density, and then we carry out the integration. We also define the standard deviation, same way as in the discrete case. We have a property about the variance of linear functions of a random variable, namely that if we add a constant to a random variable, this has no effect on the variance, but if we multiply a random variable by a constant, the variance gets multiplied by the square of that constant. Finally, when calculating the variance, it is often convenient to use this alternative formula, in which the variance is calculated by finding the expected value of the square of the random variable and also using the expected value of the random variable but squared and subtracted from the first term. This relation and this relation are both derived exactly the same way as in the discrete case, and there is no reason to repeat those derivations. As an example of a mean variance calculation, we will now consider the continuous uniform random variable, which we have introduced a little earlier. This is the continuous analog of the discrete uniform, for which we have already seen formulas for the corresponding mean and variance. So let us now calculate the mean or expected value for the continuous case. The mean is defined as an integral that ranges over the entire real line. On the other hand, we recognize that the density is equal to 0 outside the interval from a to b, and therefore there is going to be no contribution to the integral from those x's outside that interval. This means that we can integrate just over the interval from a to b, and inside that interval the value of the density is 1 over b minus a. We can carry out this integration and find an answer equal to a plus b over 2, which interestingly also happens to be the same as in the discrete case. In fact, we could find this answer without having to run this integration. We could just recognize that this PDF is symmetric around the midpoint of the interval, and the midpoint is a plus b over 2. We now continue with what is involved in the calculation of the expected value of the square of the random variable. Using the expected value rule, this is the integral of x squared times the density, but because of the same argument as before, we only need to integrate from a to b. We can evaluate this integral, and the answer turns out to be 1 over b minus a times b cubed over 3 minus a cubed over 3. The reason why these cubic terms appear is that the integral of the x squared function is x cubed divided by 3. Now that we have this quantity available, we are ready to calculate the variance using this alternative formula, which, as we have often discussed, usually provides us a quicker way to carry out the calculation. We take this term, insert it here, we take the square of this term, insert it here, carry out some algebra, and eventually we find an answer which is equal to b minus a squared over 12. And this is the formula for the variance of a uniform random variable. We can take the square root of this expression to find the standard deviation, and the standard deviation is going to be b minus a divided by the square root of 12. A few observations. First, the formula looks quite similar to the formula for the variance that we had in the discrete case, except that in the discrete case we have this extra additive factor of 2. More interestingly, and perhaps more important, is that the standard deviation is proportional to the width of this uniform. The wider it is, the larger the standard deviation will be. And this conforms to our intuition that the standard deviation captures the width of a particular distribution. And the variance, of course, becomes larger when the width is larger, and as far as the variance is concerned, it increases with the square of the length of the interval over which we have our distribution. We now introduce a new type of random variable, the exponential random variable. It has a probability density function that is determined by a single parameter lambda, which is a positive number, and the form of the PDF is as shown here. Note that the PDF is equal to 0 when x is negative, which means that negative values of x will not occur, they have 0 probability, and so our random variable is a non-negative random variable. The shape of the PDF is as shown in this diagram. It's 0 for negative values, and then for positive values it starts off at a value equal to lambda. This is because if you plug in x equal to 0 in this expression, you get lambda times e to the 0, which leaves you just with lambda. So it starts off at lambda and then it decays at the rate of lambda. Notice that when lambda is small, the initial value of the PDF is small, but then the decay rate is also small, so that the PDF extends over a large range of x's. On the other hand, when lambda is large, then the PDF starts large, so there's a fair amount of probability in the vicinity of 0, but then it decays pretty fast, so there's much less probability for larger values of x. Another observation to make is that the shape of this exponential PDF is quite similar to the shape of the geometric PDF that we have seen before, the only difference being that here we have a discrete distribution, but here we have a continuous analog of that distribution. Let us now carry out a calculation. Let us fix some positive number a, and let us calculate the probability that our random variable takes a value larger than or equal to a. So what we're trying to do is to calculate the probability that the random variable falls inside this interval from a to infinity. Whenever we have a PDF, we can calculate the probability of falling inside an interval by integrating over that interval the value of the PDF. Therefore, we have to calculate this particular integral. And at this point, we can recall a fact from calculus, namely that the integral of the function e to the ax is 1 over a times e to the ax. We can use this fact by making the correspondence between a and minus lambda. And using this correspondence, we can now continue the calculation of our integral. We have a factor of lambda, and then a factor of 1 over a, where a stands for minus lambda. So we get a minus 1 over lambda. And then the same exponential function, e to the minus lambda x. And because the range of the integration is from a to infinity, we need to evaluate the integral at a and infinity and take the difference. Now this lambda cancels that lambda. We're left with a minus sign, and from the upper limit we get e to the minus lambda times infinity. And then from the second term we have a minus sign that cancels with that minus sign and gives us a plus term, plus e to the minus lambda a. Now e to the minus infinity is 0, And so we're left just with the last term, and the answer is e to the minus lambda a. So this gives us the tail probability for an exponential random variable. It tells us that the probability of falling higher than a certain number falls off exponentially with that certain number. An interesting additional observation: if we let a equal to 0 in this calculation, we obtain the integral of the PDF over the entire range of x's, and in that case this probability becomes e to the minus lambda 0, which is equal to 1. So we have indeed verified that the integral of this PDF is equal to 1, as it should be. Now let us move to the calculation of the expected value of this random variable. We can use the definition. Since the PDF is non-zero only for positive values of x, we only need to integrate from 0 to infinity. We integrate x times the PDF. And this is an integral that you may have encountered at some point before. It is evaluated by using integration by parts, and the final answer turns out to be 1 over lambda. Regarding the calculation of the expected value of the square of the random variable, we need to write down a similar integral, except that now we will have here x squared. This is just another integration by parts, only a little more tedious, and the answer turns out to be 2 over lambda squared. Finally, to calculate the variance, we use the handy formula that we have. And the expected value of x squared is this term. The expected value of x is this term. When we square it, it becomes similar to this term, but we have here a 2, there we have a 1, and so we're left with just 1 over lambda squared. And this is the variance of the exponential random variable. Notice that when lambda is small, the PDF, as we discussed before, falls off very slowly, which means that large x's are also quite possible, and so the average of this random variable will be on the higher side. The PDF extends over a large range, and that translates into having a large mean. And because when that happens, the PDF actually spreads, the variance also increases, and this is reflected in this formula for the variance. The exponential random variable is in many ways similar to the geometric. For example, the expression for the mean, which is 1 over lambda, can be contrasted with the expression for the mean of the geometric, which is 1 over p. And the relationship between these two distributions, the discrete and the continuous analog, is a theme that we will revisit several times. At this point, let me just say that the exponential random variable is used to model many important and real-world phenomena. Generally, it models the time that we have to wait until something happens. In the discrete case, the geometric random variable models the time until we see a success for the first time. In the continuous case, an exponential can be used to model the time until a customer arrives, the time until a light bulb burns out, the time until a machine breaks down, the time until you receive an email, or maybe the time until a meteorite falls on your house. We have seen that several properties, such as for example linearity of expectations, are common for discrete and continuous random variables. For this reason, it would be nice to have a way of talking about the distributions of all kinds of random variables without having to keep making a distinction between the different types, discrete or continuous. This leads us to describe the distribution of a random variable in a new way in terms of a so-called cumulative distribution function, or CDF for short. A CDF is defined as follows. The CDF is a function of a single argument, which we denote by little x in this case, and it gives us the probability that the random variable takes a value less than or equal to this particular little x. We will always use uppercase F's to indicate CDFs, and we will always have some subscripts that indicate which random variable we're talking about. The beauty of the CDF is that it just involves a probability, a concept that is well defined no matter what kind of random variable we're dealing with. So in particular, if x is a continuous random variable, the probability that x is less than or equal to a certain number, this is just the integral of the PDF over that range from -infinity up to that number. As a more concrete example, let us consider a uniform random variable that ranges between a and b, and let us try to plot the corresponding CDF. The CDF is a function of little x, and the form that it takes depends on what kind of x we're talking about. If little x falls somewhere here to the left of a, and we ask for the probability that our random variable takes values in this interval, then this probability will be 0 because all of the probability of this uniform is between a and b. Therefore, the CDF is going to be 0 for values of x less than or equal to a. How about the case where x lies somewhere between a and b? In that case, the probability that our random variable falls to the left of here, this is whatever mass there is under the PDF when we consider the integral up to this particular point. So we're looking at the area under the PDF up to this particular point x. This area is of the form the base of the rectangle, which is x minus a, times the height of the rectangle, which is 1 over b minus a. This is a linear function in x that takes the value of 0 when x is equal to a, grows linearly, and when x reaches a value of b, it becomes equal to 1. How about the case where x lies to the right of b? We're talking about the probability that a random variable takes values less than or equal to this particular x. But this includes the entire probability mass of this uniform. We have unit mass on this particular interval, so the probability of falling to the left of here is equal to 1. And this is the shape of the CDF for the case of a uniform random variable. It starts at 0, eventually it rises, and eventually it reaches the value of 1 and stays constant. Coming back to the general case, CDFs are very useful because once we know the CDF of a random variable, we have enough information to calculate anything we might want to calculate. For example, consider the following calculation. Let us look at the range of numbers from -infinity to 3 and then up to 4. If we want to calculate the probability that x is less than or equal to 4, we can break it down as the probability that x is less than or equal to 3, this is one term, plus the probability that x falls between 3 and 4, which would be this event here. So this equality is true because of the additivity property of probabilities. This event is broken down into two possible events, either x is less than or equal to 3 or x is bigger than 3 but less than or equal to 4. But now we recognize that if we know the CDF of the random variable, then we know this quantity, we also know this quantity, and this allows us to calculate this quantity. So we can calculate the probability of a more general interval. So in general, the CDF contains all available probabilistic information about a random variable. It is just a different way of describing a probability distribution. From the CDF, we can recover any quantity we might wish to know. And for continuous random variables, the CDF actually has enough information for us to be able to recover the PDF. How can we do that? Let's look at this relation here and let's take derivatives of both sides. On the left, we obtain the derivative of the CDF, and let's evaluate it at a particular point x. What do we get on the right? By basic calculus results, the derivative of an integral with respect to the upper limit of the integration is just the integrand itself, so it is the density itself. So this is a very useful formula which tells us that once we have the CDF, we can calculate the PDF. And conversely, if we have the PDF, we can find the CDF by integrating. Of course, this formula can only be correct at those places where the CDF has a derivative. For example, at this corner here, the derivative of the CDF is not well defined. We would get a different value if we differentiate from the left, a different value when we differentiate from the right, so we cannot apply this formula. But at those places where the CDF is differentiable, at those places we can find the corresponding value of the PDF. For instance, in this diagram, at this point the CDF is differentiable. The derivative is equal to the slope, which is this quantity, and this quantity happens to be exactly the same as the value of the PDF. So indeed here we see that the PDF can be found by taking the derivative of the CDF. Now, as we discussed earlier, CDFs are relevant to all types of random variables, so in particular they are also relevant to discrete random variables. For a discrete random variable, the CDF is of course defined the same way, except that we calculate this probability by adding the probabilities of all possible values of the random variable that are less than the particular little x that we are considering. So we have a summation instead of an integral. Let us look at an example. This is an example of a discrete random variable described by a PMF, and let us try to calculate the corresponding CDF. The probability of falling to the left of this number, for example, is equal to 0, and all the way up to 1, there is 0 probability of getting a value for the random variable less than that. But now, if we let x to be equal to 1, then we're talking about the probability that the random variable takes a value less than or equal to 1. And because this includes the value of 1, this probability will be equal to 1/4. This means that once we reach this point, the value of the CDF becomes 1/4. At this point, the CDF makes a jump. At 1, the value of the CDF is equal to 1/4. Just before 1, the value of the CDF was equal to 0. Now, what's the probability of falling to the left of, let's say, 2? This probability is again 1/4. There's no change in the probability as we keep moving inside this interval. So the CDF stays constant until at some point we reach the value of 3. And at that point, the probability that the random variable takes a value less than or equal to 3 is going to be the probability of a 3 plus the probability of a 1, which becomes 3/4. For any other x in this interval, the probability that the random variable takes a value less than this number will stay at 1/4 plus 1/2. So the CDF stays constant. And at this point, the probability of being less than or equal to 4, this probability becomes 1. And so the CDF jumps once more to a value of 1. Again, at the places where the CDF makes a jump, which one of the two is the correct value? The correct value is this one, and this is because the CDF is defined by using a less than or equal sign in the probability involved here. So in the case of discrete random variables, the CDF takes the form of a staircase function It starts at 0, it ends up at 1. It has a jump at those points where the PMF assigns a positive mass, and the size of the jump is exactly equal to the corresponding value of the PMF. Similarly, the size of the PMF here is 1/4, and so the size of the corresponding jump at the CDF will also be equal to 1/4. CDFs have some general properties, and we have seen a hint of those properties in what we have done so far. So the CDF is by definition the probability of obtaining a value less than or equal to a certain number little x. It's the probability of this interval. If I were to take a larger interval and go up to some larger number y, this would be the probability of a bigger interval, so that probability could only be bigger. And this translates into the fact that the CDF is a non-decreasing function. If y is larger than or equal to x, as in this picture, then the value of the CDF evaluated at that point y is going to be larger than or equal to the CDF evaluated at that point little x. Other properties that the CDF has is that as x goes to infinity, we're talking about the probability essentially of the entire real line, and so the CDF will converge to 1. On the other hand, if x tends to minus infinity, so we're talking about the probability of an interval to the left of a point that's all the way out, further and further out, that probability has to diminish and eventually converge to 0. So in general, CDFs asymptotically start at 0. They can never go down, they can only go up, and in the limit as x goes to infinity, the CDF has to approach 1. Actually, in the examples that we saw earlier, it reaches the value of 1 after a certain finite point, but in general, for general random variables, it might only reach the value of 1 asymptotically. We now introduce normal random variables, which are also often called Gaussian random variables. Normal random variables are perhaps the most important ones in probability theory. They play a key role in the theory of the subject, as we will see later in this class in the context of the central limit theorem. They are also prevalent in applications for two reasons. They have some nice analytical properties, and they are also the most common model of random noise. In general, they are a good model of noise or randomness whenever that noise is due to the addition of many small independent noise terms, and this is a very common situation in the real world. We define normal random variables by specifying their PDFs, and we start with the simplest case of the so-called standard normal. The standard normal is indicated with this shorthand notation, and we will see shortly why this notation is being used. It is defined in terms of a PDF. This PDF is defined for all values of x. X can be any real number, so this random variable can take values anywhere on the real line, and the formula for the PDF is this one. Let us try to understand this formula. So we have the exponential of negative x squared over 2. Now, if we are to plot the x squared over 2 function, it has a shape of this form. And it is centered at 0. But then we take the negative exponential of this function. Now, when you take the negative exponential, whenever this thing is big, the negative exponential is going to be small. So the negative exponential would be equal to 1 when x is equal to 0. But then as x increases, because x squared also increases, the negative exponential will fall off. And so we obtain a shape of this kind, and symmetrically on the other side as well. And finally, there is this constant. Where does this constant is coming from? Well, there's a nice and not completely straightforward calculus exercise that tells us that the integral from minus infinity to plus infinity of e to the negative x squared over 2 dx is equal to the square root of 2 pi. Now, we need a PDF to integrate to 1. And so for this to happen, this is the constant that we need to put in front of this expression so that the integral becomes 1. And that explains the presence of this particular constant. What is the mean of this random variable? Well, x squared is symmetric around 0, and for this reason, the PDF itself is symmetric around 0, and therefore, by symmetry, the mean has to be equal to 0. And that explains this entry here. How about the variance? Well, to calculate the variance, you need to solve a calculus problem again. You need to integrate by parts. And after you carry out the calculation, then you find that the variance is equal to 1, and that explains this entry here in the notation that we have been using. Let us now define general normal random variables. General normal random variables are once more specified in terms of the corresponding PDF, but this PDF is a little more complicated and it involves two parameters, mu and sigma squared, where sigma is a given positive parameter. Once more, it will have a bell shape, but this bell is no longer symmetric around 0, and there is some control over the width of it. Let us understand the form of this PDF by focusing first on the exponent, exactly as we did for the standard normal case. The exponent is a quadratic, and that quadratic is centered at x equal to mu. So it vanishes when x is equal to mu and becomes positive elsewhere. Then we take the negative exponential of this quadratic and we obtain a function which is largest at x equal to mu and falls off as we go further away from mu. What is the mean of this random variable? Since this term is symmetric around mu, the PDF is also symmetric around mu, and therefore the mean is also equal to mu. How about the variance? It turns out, and this is a calculus exercise that we will omit, that the variance of this PDF is equal to sigma squared. And this explains this notation here. We're dealing with a normal that has a mean of mu and a variance of sigma squared. To get a little bit of understanding of the role of sigma in the form of this PDF, let us consider the case where sigma is small and see how the picture is going to change. When sigma is small and we plot the quadratic, sigma being small means that this quadratic becomes larger, so it rises faster, so we get a narrower quadratic, and in that case the negative exponential is going to fall off much faster. So when sigma is small, the PDF that we get is a narrower PDF, and that reflects itself into the property that the variance will also be smaller. An important property of normal random variables is that they behave very nicely when you form linear functions of them. And this is one of the reasons why they're analytically tractable and analytically very convenient. Here is what I mean. Let us start with a normal random variable with a given mean and variance, and let us form a linear function of that random variable. What is the mean of y? Well, we know what it is. We have a linear function of a random variable. The mean is going to be a times the expected value of x, which is mu, plus b. What is the variance of y? We know what is the variance of a linear function of a random variable. It is a squared times the variance of x, which in our case is sigma squared. So there is nothing new so far, but there is an additional important fact. The random variable y Of course, has the mean and variance that we know it should have, but there is an additional fact, namely that y is a normal random variable. So normality is preserved when we form linear functions. There's one special case that we need to pay some attention to. Suppose that a is equal to 0. In this case, the random variable y is just equal to b. It's a constant random variable. It does not have a PDF. It is a degenerate discrete random variable. So could this fact be correct that y is also normal? Well, we'll adopt this as convention. When we have a discrete random variable, which is constant, it takes a constant value, we can think of this as a special degenerate case of the normal with mean equal to b and with variance equal to 0. Even though it is discrete, not continuous, we will still think of it as a degenerate type of a normal random variable, and by adopting this convention, then it will always be true that a linear function of a normal random variable is normal, even if a is equal to 0. Now that we have the definition and some properties of normal random variables, the next question is whether we can calculate probabilities associated with normal random variables. This will be the subject of the next segment. We have claimed that normal random variables are very important, and therefore we would like to be able to calculate probabilities associated with them. For example, given a normal random variable, what is the probability that it takes a value less than 5? Unfortunately, there are no closed form expressions that can help us with this. In particular, the CDF, the cumulative distribution function of normal random variables, is not given in closed form, but fortunately, we do have tables for the standard normal random variable. These tables, which take the form shown here, give us the following information. If we have a normal random variable, which is a standard normal, they tell us the values of the cumulative distribution function for different values of little y. In terms of a picture, if this is the PDF of a standard normal and I give you a value little y, I'm interested in the corresponding value of the CDF, which is the area under the curve. Well, that value, the area under this curve, is exactly what this table is giving to us. And there's a shorthand notation for referring to the CDF of the standard normal, which is just phi of y. Let us see how we use this table. Suppose we're interested in phi of 0, which is the probability that our standard normal takes a value less than or equal to 0. Well, by symmetry, since the PDF is symmetric around 0, we know that this probability should be 0.5. Let's see what the table tells us. Well, 0 corresponds to this entry, which is indeed 0.5. Let us look up the probability that our standard normal takes a value less than, let's say, 1.16. How do we find this information? 1 is here, and 1.1 is here. 1.1, and then we have a 6 in the next decimal place, which leads us to this entry. And so this value is 0.8770. Similarly, we can calculate the probability that the normal is less than 2.9. How do we look up this information? 2.9 is here. We do not have another decimal digit, so we're looking at this column, and we obtain this value, which is 0.9981. And by looking at this number, we can actually tell that a standard normal random variable has extremely low probability of being bigger than 2.9. Now notice that the table specifies phi of y for y being non-negative. What if we wish to calculate the value, for example, of phi of minus 2? in terms of a picture. This is a standard normal. Here is -2. And we wish to calculate this probability. There's nothing in the table that gives us this probability directly, but we can argue as follows. The normal PDF is symmetric, so if we look at 2, then this probability here, which is phi of -2, is the same as that probability here of that tail. What is the probability of that tail? It's 1, which is the overall area under the curve, minus the area under the curve when you go up to the value of 2. So this quantity is going to be the same as phi of -2, and this one we can now get from the tables. It's 1 minus, let us see, 2 is here, it's 1 minus 0.9772. The standard normal table gives us probabilities associated with the standard normal random variable. What if we're dealing with a normal random variable that has a mean and a variance that are different from those of the standard normal? What can we do? Well, there's a general trick that you can do to a random variable, which is the following. Let us define a new random variable y in this fashion. Y measures how far away is x from the mean value, but because we divide by sigma, the standard deviation, it measures this distance in standard deviations. So if y is equal to 3, it means that x is 3 standard deviations away from the mean. In general, y measures how many deviations away from the mean are you. What properties does this random variable have? The expected value of y is going to be equal to 0 because we have x and we're subtracting the mean of x, so the expected value of this term is equal to 0. How about the variance of y? Whenever we multiply a random variable by a constant, the variance gets multiplied by the square of that constant, so we get this expression. But the variance of x is sigma squared, so this is equal to 1. So starting from x, we have obtained a closely related random variable y that has the property that it has 0 mean and unit variance. If it also happens that x is a normal random variable, then y is going to be a standard normal random variable. So we have managed to relate x to a standard normal random variable, and perhaps you can rewrite this expression in this form: x equals to mu plus sigma y, where y is now a standard normal. So instead of doing calculations having to do with x, we can try to calculate in terms of y, and for y we do have available tables. Let us look at an example of how this is done. The way to calculate probabilities associated with general normal random variables is to take the event whose probability we want to calculate it and express it in terms of standard normal random variables and then use the standard normal tables. Let us see how this is done in terms of an example. Suppose that x is normal with mean 6 and variance 4, so that the standard deviation sigma is equal to 2. And suppose that we want to calculate the probability that x lies between 2 and 8. Here's how we can proceed. This event is the same as the event that x minus 6 takes a value between 2 minus 6 and 8 minus 6. This event is the same as the original event we were interested in. We can also divide both sides of this inequality by the standard deviation, and the event of interest has now been expressed in this form. But at this point, we recognize that this is of the form x minus mu over sigma. So this random variable here is a standard normal random variable. So the probability that x lies between 2 and 8 is the same as the probability that a standard normal random variable, call it y, falls between, this number is minus 4 divided by 2, that's minus 2, then y less than 1. And now we can use the standard normal tables to calculate this probability. We have here 1 and here we have minus 2, and we want to find the probability that our standard normal falls inside this range. This is the probability that it is less than 1, but we need to subtract the probability of that tail so that we're left just with this intermediate area. So this is the probability that y is less than 1 minus the probability that y is less than minus 2. And finally, as we discussed earlier, the probability that y is less than minus 2, this is 1 minus the probability that y is less than or equal to 2. And now we can go to the normal tables, identify the values that we're interested in, the probability that y is less than 1, the probability that y is less than 2, and plug these in, and this gives us the desired probability. Again, the key step is to take the event of interest, and by subtracting the mean and dividing by the standard deviation, express that same event in an equivalent form, but which now involves a standard normal random variable. And then finally use the standard normal tables.